Welcome to iLectureOnline, and here's a very interesting combination for you. We have a combination of a mirror and a lens. So first, if I put the object over here, the rays of the object will pass through the lens. It's a converging lens, so the rays will come together, but then they will bounce off of this mirror and form a second image. So again, the way you do a lens and mirror combination is exactly the same the way you do a lens-lens combination. You first form an image caused by the first lens, totally ignoring the mirror, and then you use that image of the first lens as the object of the mirror, and then use that to find the image of the mirror itself. Now, since this is a converging mirror, the focal length of the converging mirror is positive. This is a converging lens, so that focal length of the lens is also positive. This is also known as a concave mirror. So let's go ahead and get started. The first thing we want to do is draw the rays caused by the first object. The first ray would be parallel to the normal until we hit the lens. The ray will then bend through the focal point on the other side. And so that would be ray number one. The second ray would be drawn through the focal point on the front of the lens right here and continue on until we hit the lens. The ray will then bend, continue parallel to the normal over here like this. And so the image of the first lens would be formed somewhere back here. Call that image 1. To find out exactly where that is located, we use our equation. We can say that S1 prime is equal to S1 F1 over S1 minus F1. And so S1 was 50 centimeters, F1 was 20 centimeters. So this would be 50 minus 20, or 1,000 divided by 30, which is 33.3 centimeters. So that would be S1 prime. Notice that it's a positive image distance. Positive means that it's a real image relative to the mirror. Relative to the lens. And let's see here. We want to know magnification. M1 is equal to negative S1 prime over S1, which is a negative 33.3 divided by 50, which is a negative, looks like 2/3. Negative 2/3. That means the image is only 2/3 the size of the original object. Negative means that the image is inverted. And that you can see that would be the case. So that would be an inverted image. And of course, that would indicate that it's a real image relative to the lens. All right, so now how do we find the second image, this one caused by the mirror? You can see, of course, as the rays hit the mirror, they're not going to continue this way. They're simply going to bounce off the mirror and do something else. And so let's find out what that means. First of all, we know that this here is the distance from the lens to the first image. We found that to be 33.3 centimeters. So S1 prime is equal to 33.3 centimeters, which means the distance from the image to the mirror is that minus the 10 centimeters. So let's say that the distance between these two is 10 centimeters. So that would make this distance here 23.3 centimeters. And since the image of the first lens now becomes the object of the mirror, that would place the object behind the mirror. Of course, typically that is not possible. If you just have a single mirror and you place an object behind the mirror, you're not going to see any images. But this one is caused by rays coming from the left, hitting the mirror, that would normally put an image there, and so therefore we can use that technique. And so now we're going to use the equation to find the second image. So this is S2 prime is equal to S2 F2 divided by S2 minus F2. And so this is equal to S2, which is a minus, S2 is equal to minus 23.3 centimeters because it's behind the mirror. So minus 23.3. Multiply that times F2, which was a positive 30, divided by S2, which is a minus 23.3, minus 30 of the focal length of the mirror. All right. Grabbing a calculator, 23.3 times 30, and divide that by, looks like 6.7. And that would be, oh, no, we're adding those two together, aren't we? So it would be divided by 53.3. And that's a negative. And that would be negative divided by negative, which is a positive. So this is equal to a positive 13.1 centimeters. All right, now that's an interesting result. Notice that this is a positive image distance. And we're dealing with a mirror here. So with a mirror, a positive image just means it's in front of the mirror. That means the image is somewhere around this location right there. Now we don't know yet if it's upright or upside down. We'll figure that out in just a moment. But this would make that into a real image because it's in front of the mirror. All right. Secondly, we want to find the magnification. So M2 is equal to minus S2 prime over S2. S2 was 13.1, so that's minus 13.1 divided by S2. S2 was a minus 23.3. So let's figure out what that is. So divided by 23.3, that would be minus, no, it would be plus, because 0.56. Okay, now, does that mean that the image is right side up or inverted? Well, at first thought, you'd say, hey, you have a positive magnification, therefore, yes, it's upright, but no. This is relative to the object that caused the image, and since the object is already inverted, that means it's not re-inverted, so it stays inverted. That means this is an inverted image. Same orientation as the object that caused it. So now we can say that it's over here, it's inverted, it's about half the size of the image over here, and we know that the image over here was about 2/3 the size of this image right here. So it's a relatively small image in this direction. So there's image 2. And this distance right here is 13.1 centimeters, which places a 13.1 centimeters in front of the mirror, or 3.1 centimeters in front of the first lens. It is inverted. The total magnification, M total, is equal to M1 times M2, which is equal to minus 2/3 multiplied times a 0.56. Not a lot of light in here anymore, so times 2 divided by 3 equals, and it's about a minus 0.38. And that's the total magnification of the second image relative to the original object. And that is how you work with a lens-mirror combination.